So this is the list of things I hope we can get through today, all right? As close as we can. So the first thing we'll do, we'll start off right here and try to talk about these. Then we can just work our way through. So first let me explain what an inverse is. You already know what a function is. Actually, let me start over here and work our way across. So I could have a function like that. You know what to do with that now? Okay? And you're comfortable with the notation? You don't want to do with that or... Yeah, okay. Anyhow, if I were to take a number, let's just pick a 4. So if I were to plug a 4 into here, then I'd have 2 times 4 plus 3. So 8. So I will get 11, right? And then if I were to take, and if I had some other function, we'll find that in a moment, okay? When I use this -1 like that, it's not an exponent, okay? It just means the math guys didn't want to write out the word inverse, okay? So that 1 really means inverse. That's how we should read it. So it's not mathematical, even though it looks that way, okay? It's our shorthand way of just writing inverse. So if I had an inverse function, and I were to plug the 11 into that, the answer that's going to pop out will be a 4. Okay? So an inverse function undoes what another function did. Okay? So if I plug any number into my original function, I'll get some answer, take that answer, plug it into whatever the inverse function is, and it will undo it. Okay? What's that?
How do you put that in the calculator?
Well, at this point, you can't. Right. There's a lot of... I need to tell you a lot more about this. I'm just saying there's some function out there that undoes what this one just did. Okay? This one multiplied by 4 and added 3 to it. We're going to undo that. So we need to find that function that will undo it. Okay? So at this point, yeah, you don't know how to get there, and that's what we'll be doing. Okay? In fact, another way we like to write this, it almost gives you a little picture of what's going on. These could be circuits, they could be subroutines in programs. So again, if I were to take my 4, so here's my f of x, and inside, it's 2x plus 3, cranks out our 11. So now we take the 11 and we plug it into our inverse function. And again, we don't know what that is yet, but we do know that if it is an inverse function, it simply undoes what the first one did. Okay? So, I picked a different example, but that's okay. So let me show you how to find, well, one question would be, are these two functions inverses? Or, how can we find the inverse, okay? So let's use that example up there. If I have f of x equals 2x minus 5, here are the steps to find an inverse. Okay? So first thing is, instead of having the f of x symbol, we'll just stick in a y. Second step is we are going to swap x and y. Literally, we just put the x over here, put the y over here. Okay? Now, what we need to do is solve it again for y. In other words, we want to do some algebra here so that we end up with y equals again. Okay? So let's just do those. We would probably want to add 5. So now we have that x plus 5 is equal to 2y. And we would divide by the 2, divide both terms by the 2. And do you mind if I just flip this whole thing? Okay with me doing that? Okay. So then, of course, I end up with y equals x plus 5 over 2. So, or better yet, I'll write it out this way. The inverse function is equal to x plus 5 over 2. Okay. So you could imagine then if we wanted to do it for this little equation, we could go through the exact same steps.
X separate from the 5 over 2. Yeah, like, could you have x equals, y equals x plus and then 5 over 2? Would that be the same thing, or?
Let me see. You mean that?
Yeah.
That would be different.
Would be different.
Yeah, because we are actually dividing both terms by the 2. Did I answer your question on that?
Yep.
Okay. Yeah, that's good. A good distinction to have. So there's how you would find an inverse. Get rid of the f of x, put in a y, swap x and y, and then solve again till we have y equals. Okay? And so we're saying that little thing is inverse. The inverse function that we started with is that. Okay? So of course I could plug in, if I were to plug in any number here, this would undo it and give me that same number back. There's one more way we could check. So in this case, what we did is we found the inverse of this, and it was the same as that, right? So that's how we say that the g of x, have you seen that? Sometimes we normally say f of x, sometimes we'll say g of x, h of x, and there's no good reason for picking those letters, okay? But for some reason we never use s of x. Probably never use s of x, okay? We tend to use f, g, h, and normally don't want to go beyond that. So here's a more thorough way of finding if these two were inverses, okay? All right, here we go. So remember, don't write this down, but one of the things we were doing a little bit ago is we would say, well, what about finding a plus 2? We would actually plug this thing into our function, right? And you had to distribute and simplify again, right? Remember doing that? Okay, so with that in mind, what we would like to find is this. In other words, what I'm doing is I'm taking g of x and I'm sticking it inside of f of x. Okay? I like this notation. The book will tend to do this. Well, actually, it depends on the book. They tend to go... I'm going to forget what their book does, which isn't all bad. F, G. Sometimes they'll write it like that, okay? This is an open circle, so you may run into that a little bit. I think this notation is much more intuitive. You can see that G is getting plugged into the F one, right? Okay. But I just wanted to warn you that notation is out there as well. It means the same thing. I just don't like it as much. Okay. What's that?
What was it?
Oh, sorry. It is F dot G, parentheses around it with the X outside like that. That is simply another way to write this. And unfortunately, there's another thing that's very similar to that can easily be confused with it. So it's another good reason not to use it. So I won't be using that one. I just thought I should warn you that it exists. So here's how we do this. So first I'm going to write out my function f, which is 2x minus 5. All right with that? And now I'm going to plug the g of x, which is this, right into there. So I'm going to put my x plus 5 over 2 like that. So you can see this right here is the g of x. Right? So again, here's f of x. It's 2 times x minus 5. So I've rewritten the f, but instead of using the variable x right here, I left a big blank. And where the x was, I put the g. Okay? So now we just need to try to simplify this a little bit. So you could multiply the 2 like that, but can everyone see what's really going to happen first is that? The 2 here will cancel that denominator. So now I would be left with x plus 5 there, and minus 5 And now you can see that, of course, those will cancel, right? And we're just left with x. So if you can plug one function inside of the other function and simplify it, and you come up with just x left over, we say that they're inverse. They undo each other. Okay? This function did some stuff to the x. It doubled it, subtracted 5. This function adds 5 to it and divides by 2, right? So what we're saying is if you try to do both at the same time, nothing happens. X stays x. The number 4 plugged into there would come right back out as a number 4. Okay. So this is the second way you could check to see if something is an inverse. It doesn't give you the inverse. Like over here, the cool thing is that you actually find what the inverse is. And that's sometimes what they want. But this is another way you could check. And I'd like you to be able to do both of those. Okay? So when you're doing the homework, don't always use the easiest one you know. Okay? I would like you to be familiar with a few different approaches. Okay? And then we should talk about this graphically. Let's see here. So we've been looking at this inverse stuff algebraically. Let's do it just a little bit graphically, okay? I'm not going to tell you what this is, I'm just saying, if I were to graph it, and let's say it looked like this. Okay? The question would be, what would the graph of the inverse look like? Okay? And here's what you do is you try to imagine, here's a line going through the origin, 45 degrees, okay? The inverse graph of this would be something, try to flip it across, mirror it across the line, right? So you can imagine I would start here and go kind of like that. See how it mirrors across the line nicely? So that's how you could simply say, these must be inverse functions because they would mirror across. Something else that happens, though, let's just look at the points. Let's see. This point right here. Actually, let me try to keep my color code going on. So maybe that is 3, 2. Could be, right? Then if that's true, then I should be able to go over here and find the same point, but it will be at 2, 3. Okay? And I should also be able to do the same thing down here. I said, okay, this looks like maybe 0.5, -5. Could be, right? Then I should also have in this graph over here another point that is at -5, 0.5. Okay? So another way that you might see, if we were to have a set of points, 2, 3, oh, don't need that comma. So if this is a function, right, described by those set of points, then we can tell right away that the inverse function is going to have those exact same points, but everything's swapped. Okay? So it's literally going to be as simple as 3, 2, 5, 4, 7, 6. So now we have 3 ways to talk about inverses. We can do it algebraically, right? You know how to calculate an inverse of an equation? You could look at a graph and imagine just trying to mirror it across, right? That would be a graphical representation of it. And then we could also look at a set of points. And all you're doing is you're just switching. Okay? So I think it's easy enough. It's just trying to get these all sorted out. Okay? So it looks like I'm getting ahead of my slide, which isn't also bad. So you could do that algebraically. Okay, let's do a little harder inverse here, okay? So first step would be what? Again, we're just going to find the inverse. Okay. Next step.
Switch the y and the x.
Okay, so now this will become x equals 2y squared minus 4. Now what? Solve for y. So I'm going to go plus 4, plus 4. Now what? Good. Now what?
Square root each side.
Right, since that's, and if that were a cube, you'd do like cubed root. Does everyone know how to do a cubed root maybe? Okay, so we'll do square root. So now we're saying then the inverse function would be equal to the square root of x plus 4 over 2. This one here, do you think you know how you would probably start on that, or is this something we should try to do? It's a little different. Same steps, so. Guys, would you like to do it or not worry about this one? Do it? Okay. So here we start off with f of x. And of course then we'll swap our x and y's. Swap these guys. Okay, now what?
Do the cube root.
Cubed root, yep. Yeah, kind of like we did in this step down here, right? To undo that square. So we take the cubed root. Again, I hope you've done that one before. That's not your first time seeing that. And here we're going to take the cubed root. And all that really happens is these undo each other, right? It's kind of like saying the square root of 4 squared. So sure, we could make that square root of 16, which is 4, right? But if you just recognize that this is doing the opposite of that, you can simply cancel it and know it's a 4. So it's kind of a, again, I think you would have seen that before. So now over here we have cubed root of x equals, so again, these cancel each other out, so we have y minus 9. So now the next step is easy, right? Plus 9. So then we were saying that y would be equal to the cubed root of x plus the 9 like that. Or we could use our inverse notation like that. Okay. All right, so here's kind of the last group, and again, there's lots of vocabulary in here. So sometimes we ask ourselves the question, and you probably don't do this very often, is my guess. You look at something and say, well, does it always have an inverse? You may wonder that, right? You probably, I'm sure, haven't wondered that before and may not want to wonder it again. But so that's one of the questions we wonder. It's like, well, before we even do it, can we tell if there's an inverse? The other question, though, that they want to know a lot of times is, okay, let's say we find the inverse, but will the results be a function also? And you remember how we determined if something were a function or not, right? You do that vertical line test. There's only, one x value always gives you exactly one y value out, right? Okay. So when we talk about this thing here, there's the key word, this phrase, one-to-one. What we want to be able to know is, by looking at, just right there without doing the math, if we did find the inverse, and if we made a graph of the inverse, okay, would it be a function? In other words, could we do the vertical line test and pass, right? Okay. So there's a couple of things to this. One is this horizontal line test, or this idea that it's either always increasing or decreasing, okay? So let's pick just a little different equation here. Actually, let's just do it graphically a couple times. So let's say here's my function, and it does that. Well, actually, first, does everyone agree that is a function? You can see how I could check along the vertical, and it only crosses the graph at one point, right? At a time. So it is a function the way I drew it. The horizontal line test says now, okay, let's check horizontally. Does the same thing apply? If I look horizontally across my graph, do I ever cross the graph more than once? In this case, no. So that means that the results would be, my inverse would also be a function. Okay? Again, now this is the graph of the original function. We haven't found the inverse. We don't know what the inverse looks like. But we can tell just by doing the horizontal line test that when we get there, it will also be a function. Okay with that? One other way you can kind of tell is this idea of that it's always increasing or decreasing. So like here, I'm increasing. So it needs to be always increasing a little bit. If I were to, like right in here, have a flat spot, or maybe even dip and then continue up. So now this graph would still be a function, right? But notice now if I tried to do the horizontal line test, right there I would cross, I'd cross two places, right? Or in fact, where it's at right there through that flat spot, I would cross for quite a while, right? So in this case, we'd say it doesn't pass the horizontal line test, which means that inverse, if we were to go find it, it's not going to be a function. Okay? Or the other phrase we'll use is, it's not one-to-one. Okay? So let's go a little farther on that. Remember we said, okay, here's the domain, and here's the range, right? And we said, let's put some numbers in here. 2, 3, 4, and over here we put 5, 6, 7, right? So when we talked about functions, we said this 2, it can go to the 5, and maybe this 3 could go down to the 7, right? So we say we have a function, right? Because one x value gives you exactly one y value. Now, in the past, we would allow this number to go to several over here, right? Okay. So now when we bring up this thing of, is it one-to-one? It needs to be able to do this both ways now. Okay? Does that make sense? Last time we only said, do the x's line up with exactly one y? And we didn't care about things coming back this way. Now we do. So we're saying the 2 comes over to here, then this maps directly back to one number there. Maybe actually here, let me put this in. Let me add one more number here. Let's see. One more color pen. Anybody else bring a? Actually, I believed you though. Okay. So again, let me just point out what would have been okay before. This 5 in the past could have gone also back to the 3. The 5 could be both ways. Here, let me erase that. Here we go. It would have been fine for the 2 to go there, the 3 to go there, 4 to go there. We'd say, yeah, we still have a function, right? And this 5 would map back to both numbers. And it was okay if all we wanted to ask the question is it a function? But now we're saying now this would be a problem. It would no longer be one-to-one. And what it means, again, is that the inverse, if we were to go around and find it, it would not be a function. Okay? So then this would be a problem line because we need it to map both ways, one-to-one. So, doing okay with that? Right. we will skip that one. And that's going to be, if we get through this one example there, that's kind of the messiest one we have. So if you encountered this and it says, are these two guys inverses? Okay? Can you tell me 3 different ways you could check? What's that? So when you say algebraically, what would you, a little farther for me? Oh, are you saying f of g of x? That? Yes, that's right. We could take the g, we could plug it into the f, and what does it have to equal to if it's a function? Yes. Or excuse me, if they're inverses, it would be equal to x. So that's one of the things we can do. What's another way we could approach this?
Just solve for one of their inverses and see if it's the other one.
Yeah. So for example, we could say, let's find the inverse of g of x. And does it equal f of x? Right? So there's another way. And again, by the way, you could do this one too if you wanted. You could plug each, it doesn't matter which way you plug them in. Okay? Same results. And then the last way, now this one isn't as convincing, but it's sure easier. Okay? Pick any number you want. Make x equal to, what's a nice number up there? How about 3? That'd be a nice number. Do you see why it'd be a nice number? If I plug 3 into the first function, what do I get? 0. Zeros are wonderful. So, but pick any number, plug it in. So we would go 3. We'd get something out, right? Well, actually, we know we're going to get that out, right? And if I plug now this into the g, hopefully it would give me a 3 back, right? That's the question. Oh. This one's still got a little bit of ink. This one's on its way out. Okay. So I'm sure everybody can do this step here. That's the easiest. This one's kind of messy, and these are both a little messy on this problem, okay? So let's do at least one of them, and I don't think we'll have time for 2. So let's find the inverse. So f of x equals, which one should we do? X minus 3 over x plus 4. So our goal is to find the inverse. We're going to do this thing here and see if it's equal to the other one. So of course, first step, y equals x minus 3 over x plus 4. Now we're going to swap all the x's and y's, right? So now this is going to be an x, but over here I have y minus, I have a y, and I have another y right here. Okay, so now we need to get the y's by themselves. And again, it's a little tricky because we have 2 of them, right? So let me walk you through these steps. We don't want the denominator here, so we're going to multiply both sides by the denominator. Okay with that step? So the reason we like that is because this simply goes away, right? So now on our right side, we just have y minus 3. On the left side, you see how I can distribute that? So we need to do that. So I have x, y plus 4x. All right. So now we're coming up on the hard step here. We need to at least get the y's on the same side, okay? So let's see. I think what I'll do, I'm going to subtract this y from here. Oh, go ahead.
Why is that?
Yeah, so the problem with solving this problem is we have y's in 2 places. We need to get them together, okay? So again, I'm going to subtract the y here. I'll subtract the y here, but I can't really combine it directly yet. I'll just have to leave it as a negative y. And I'll do one more step here. I want to get the x's away from where the y's are at, okay? So I will subtract 4x here, subtract 4x here. So now let's write out what we have. I have x, y minus y, right? Because this is gone and that's gone, right? And on this side I have a...
Wouldn't it just be x minus y? You're subtracting the y from both sides.
Well, these aren't like terms. So I just have to leave them as they are for a moment. Yeah, no, good question. Now over here, I have negative 4x minus 3. And again, these aren't like terms either, really. So I just have to leave them there, right? Okay. So here's the big trick that makes our lives easier, okay? And it's not that complicated. Notice, I could pull a y out of both terms, right? It's kind of like doing this step backwards. Greatest common factor. So I'm going to pull the y out front. So there's the x. Here's the minus sign. What's left right here? 1. That's right. Yep. And again, check yourself. If I multiplied it, I would get xy. And I'd get negative x, right? So we did a greatest common factor trick right here. Too bad I can't spell that. Okay, there we go. Equals negative 4x minus 3, so no change over there. Okay, so again, the trick here is you need to pull it out, do a greatest common factor. Okay, now that you've got this, notice we have a single y now, right? We're one easy step away. We just have to, that's multiplication, so I'm going to divide by x minus 1. And divide by x minus 1. Okay, so then of course this goes away. And what we're saying is that the inverse function of x is equal to negative 4x minus 3 divided by x minus 1. Okay. Some of you may look at the negatives and we could rewrite that one more way, but it's fine that way. Okay. But you could get the change in negative signs if you wanted to. Right? So that's really, I think, the hardest thing is finding an inverse in that kind of situation there. Right? So any questions you might want to ask about that? Again, you can find this example online, but if you've got it in your notes, I mean, when you get to the homework, you're going to see something like this, but the numbers are a little different. Same pattern, though, okay? So you should be able to follow the steps pretty close. All right? Okay. That's it.